Okay, so this video is going to be part 1 of topic number 4, which is going to go over force resultant systems. So we're going to introduce concepts surrounding moment of a force. So this will be the first time in this class we'll really get into understanding what a moment is. We're going to talk about how to calculate moments in 2D and in 3D systems. We're going to talk about the moment of a couple. And then lastly, which is also very important, we're going to introduce distributed loads and talk about how we can get the resultant of a distributed load, which is a precursor to what you'll be doing a lot in mechanics of materials and structural analysis. Okay, so to start with, a moment of a force is basically a measure that talks about the tendency of rotation. So how likely is it that a component or a system is going to experience some kind of rotation? And that's what a moment tells us, okay? So what you want to think about here is we can apply this rotation along different types of axes. So either the x-axis, the y-axis, or the z-axis. So the way a system responds to the rotation is dependent on its shape. So for example, if you're going to take your hand, let's say you take your right hand and you apply it on your left forearm and you start twisting your forearm. That is a form of moment that we actually call torque. So I'll write that down here. We'll deal with that later. We call that torque, okay? That's different than if you were to apply a force on the top of your arm and it were to experience this kind of stress from bending. So you want to think of your forearm kind of bending in a U shape. That's different than you twisting, right? So depending on the axis that you're applying that rotation, we can get different types of stress and different types of internal reactions that occur. But for right now, we're just going to focus on moments in general that kind of lead to rotation, okay? So I have this note here for you. Basically what I'm trying to say in summary is typically when a force causes rotation, we refer to that as a moment. And then when the moment causes a twisting, we refer to that as torque, okay? So I have this illustrative example here to show you what a moment is, because I know this is a new concept, but you're going to be hearing this term a lot in the next few years as you are an engineering student and then even in practice. So it's good that we familiarize ourselves as to what exactly this means. So what I want you to do is I want you to imagine that you are on one side of a door and there's someone else on the other side of the door, okay? And you guys are both pushing on the door at the doorknob on each side, okay? Now imagine that you, or that the person in front of you suddenly jumps away from the door. What's going to happen, right? The push of the other person is no longer going to have any opposition. So what's going to happen to the door? It's going to swing, right? The person still pushing on the door has now created a moment. So you see how that swing, that's a rotation. The person that's still on the door, as your weight now is no longer resisting rotation, is going to push into the door and their weight is going to cause that rotation about the hinges, and you have just created a moment, or the person has just created a moment. Okay, so this is a moment in the real world. A lot of times I'll tell you guys, like, look at your door, look at the hinges on your door, and look how that rotates if you're ever kind of confused about moment. Okay, so I'll refer to door frames a lot, or other things like your arm, or different body parts that we can talk about so that we can really understand what this rotation means and what it means in terms of the world around us. Okay, so we're going to first talk about how to formulate moments in terms of scalars, and then of course we're going to move on to vectors, because moments, they have direction and magnitude, which means we have to be considering which direction they're applied, which means we can do vector analysis for moments as well, just like we can for forces. Okay, so let's start by talking about scalar formulation. Okay, another example here is using a wrench to unscrew a bolt. So I have a picture here on the slide for you. There's a person and they are pushing on the wrench to unscrew the bolt. And as you can see, this bolt is now turning about the z-axis, right, due to that force F. So the force F is applied, we're turning the wrench about 0.0. And the magnitude of this moment, so that actual scalar quantity, is proportional to the distance d from where I'm applying the force. So I want you to think about this. Do you think it's easier to unscrew the bolt if the moment arm is longer or shorter? Does the moment arm help us create a larger moment to unscrew the bolt, or does it make it more difficult? I'm going to stay silent for a second to let you guys think about that. Okay, so I hope you guys can think about this in the real world. If you ever have unscrewed anything, if you even just assembled anything that you ordered to your house before, if you take your fingers and unscrew a bolt, it's pretty hard, right? But if you use a wrench to do it, it becomes really simple, because that moment arm, what it does, it makes our moment larger, which means I'm applying more resistance rotational force to unscrew the bolt, and it helps me in my case of getting that bolt unscrewed. Okay, so that is the reason I can actually use moment arms to my advantage. You can think about this in terms of weightlifting as well. Anytime you want to increase that stress, if you increase the moment arm, you're therefore increasing that resistance that you're building, right? So moment arm can be something very helpful that you use in different situations. Okay. Oh, I also want to bring your attention to something else here. This is very important. So I have this highlighted in red, or in this red box here. So I want you to think about this. Now, the same wrench and the same person. What happens if instead of applying the force along this line here that's shown in the top picture, what if I apply it along the axis that intersects O? Nothing happens in terms of rotation, right? I'm just applying some axial force along that bar. It's pulling, but I am not doing anything to unscrew that bolt. So this is a very important concept, basically. I have no moment arm. There is no distance that I can calculate between the force and the axis of rotation. So I am actually producing zero moment, which means I am not rotating at all. Okay, it's very important that we understand that. So, as you may understand now, to get the moment of a force, I take the force and I multiply it by my D, my moment arm. Okay, and D is the perpendicular distance from that axis of rotation, which in this case is point O, to the line of action of the force. And what does the line of action of the force mean? It means it is the line which that force acts upon. So it doesn't have to be exactly where it's applied. It just has to be anywhere on this entire line of action here, and you get this perpendicular distance from that line of action to point O. Okay, so wherever you can draw the perpendicular, that's my D, that's my moment arm. It's the shortest distance to that point of rotation. Okay, typically now, see, we have force times distance, right? So for force, we're typically using newtons or pounds. And for distance, we can use inches. I'm gonna go here in the US customary. We can use inches, we can use feet. For newtons, we're usually using meter. So you can see units of moment are either Newton meter, pound foot, pound inch. You could even see kilonewton meter, kip foot, kip inch, any of those. Okay. And the direction in terms of rotation, we either refer to it as a clockwise rotation or counterclockwise rotation. So it's a good time to remember that a clock turns in this direction, right? And so this would be clockwise, and this would be counterclockwise. And that's how we're always going to refer to the rotation of our moments and talk about how these systems, or how these forces are affecting the rotation of our system. Okay, we're also going to use the right-hand rule, so you can see here, this is a right hand showing the moment axis. We'll also use the right-hand rule primarily when we're dealing with 3D systems. We'll use the right-hand rule. Okay, so right now we're going to stick to 2D systems here. And what we want to do is to get all of the moments here, to get our resultant moment, we're going to sum up all of the forces times their distances. And that will give us this resultant moment. That's at MR about some point O. And it's good to remember that the moment is dependent on where I am summing the forces about, right? Because here I've chosen point O, so I need these perpendicular distances to point O. If I was choosing a different point, I would have different distances, and that would change my moment. So the point that I am summing moments about is very important, and that's why here I'm making it clear that these summations are about a specific point, and that point is point O. Okay, so let's go through a couple of these simple examples here. We want to determine the moment of the force about point O for each case. So let's start with case A here. Pick a different color. So I'm going to say that MO, the moment about point O, due to the force, due to this force here, is equal to, now, this is how, I'm gonna talk to you guys about rotation now, okay? So if I'm pushing down with 100 Newton force, okay, this is very important for the future of your understanding in mechanics of materials and structures and a lot of other courses. So let's get this down right now. If I'm pushing down, does everybody agree that this force, this 100-pound force around point O, is causing a rotation in this direction? Okay, that direction around point O, that direction is here. That is a clockwise rotation. It is causing a clockwise rotation. So my answer here is MO is equal to 100 newtons times, and then typically I will put the moment arm in brackets just for clarity, 2 meters, and I end up getting 200 Newton meters, and I'm going to put the little clockwise arrow so that we all know it's rotating clockwise, okay? Now this is different than, let's say we had, I'm just going to show you another example here before I move on. Let's say I have the beam like this, and I have 100 Newton force here, and point O is here. Now my rotation is going in this direction around point O. This now is counterclockwise. So you see, I just have to continue drawing the force whichever direction it's going, and that is how I'm going to figure out the direction for 2D systems. That's always how I'm going to figure out. So let's go ahead and move on to part B. We'll continue doing these and you'll hopefully get the hang of it. So here we have the moment about point O is equal to, I have a 50 Newton force and my moment arm here. So I'm going to draw the line of action of the force, goes all the way through here, and then I want the distance to point O. So perpendicular distance to point O is this 0.75, 0.75 meters, and I end up getting 37.5 Newton meters. Now for direction, let me erase this stuff so we can see which direction this is acting in. Direction, the force is going in this direction. If I just continue it about point O, I'm getting this kind of rotation. So that is clockwise. Just going to draw it in a clockwise direction, just like that. That's it. Okay. Let's do another one here for C. So what I have here, I have a 40-pound force, right? And I need to figure out what my moment is about point O. So the first thing I want to do is I want to figure out what my moment arm is. So I'm going to draw the line of action of the force, and I basically need to figure out how far that is from point O, right? This is my perpendicular distance to point O. This is the perpendicular of the line of action. So I know that it's going to be 4 feet from here to here. So I basically just need to get this horizontal distance here. Actually, they've already told me it's 2 cosine 30. Let me erase that so I have more room. Okay, so now I have MO is equal to the 40 pounds times my moment arm in brackets, which is going to be 4 plus 2 cos 30, and I get MO is equal to 229, and this is in pound feet. Now in terms of rotation, let's see what's happening here. So rotation, again, I'm going to go around this point like this, and so I have clockwise rotation again. Clockwise rotation, and that's it. Okay, so this is pretty fun, pretty simple, right? Okay, let's do 2 more of these so that we really drive this concept home. Okay, so I have MO for part D. I have a 60, oops, I don't put the pound in bracket. I have 60-pound force times my moment arm, hopefully you guys are seeing this now, they're giving me the number 1 sine 45, and I end up getting 42.4 pound-feet. And of course, I can take this around 0.0 and I get counterclockwise rotation, and that is my answer. Okay. Okay, last one right here. I have MO equals 7 kilonewtons times the distance from my force here to O is going to be actually the 4 minus 1 meters. So I end up getting 21 kilonewton meters. And then to get the rotation here, I'm going to take this around 0.0 and I end up getting counterclockwise. And that is my answer. Okay. So let's continue here. Hopefully these moment calculations make a little bit more sense and we can jump into example 2. So the first thing we're going to do, we want to determine the resultant moment of the 4 forces acting on the rod. So what we want to do here is, remember, we want to sum all of the forces times the distances to get the moments here. We want to use this equation, sum of FD. We want to sum all the forces, and this will give us that resultant moment about 0.0. Okay. Now, typically, we're always going to assume that counterclockwise is positive. So you're going to hear me saying this a lot in this class and other classes, but this is the kind of go-to, that counterclockwise is positive. Okay. So let's do this. Let's say that our MR about 0.0. Okay, I'm going to start with this 50 Newton force right here. So I'm going to say that we have 50 newtons. Now, if I'm assuming that counterclockwise is positive, I need to figure out if I should put a negative or a positive in front of the 50. So about 0.0, it's going to be traveling like this. This is clockwise. Because I'm assuming counterclockwise is positive, this is going to have a negative in front of it. Now, what is my moment arm distance from the 50 to the 0.0? It's 2 meters. And I'm done with that one. Now I need to move on to the 60. The 60 I'm going to do in green. So that I now have 60 times its moment arm. Is a 60 positive or negative? Well, 60, the line of action of the force goes through 0.0. So there's nothing there. It's plus a 0 or minus a 0. It doesn't matter, right? There's no moment arm. So I don't have to consider that one. Next one I'm going to work on is the 20, and I'll do that one in pink. So I have 20 times 20's moment arm, but is the 20 going to be positive rotation or negative rotation? So I'm going to take the 20, rotate about 0.0. This is giving me a counterclockwise, so I'm going to say positive 20. The moment arm there is going to be 3 sine 30. Right? Because I need to get this distance here. So if the hypotenuse is 3, this is 3 sine 30, and that's the distance away. And then my last one I'll do in blue, which is the 40 Newton. So I have 40 times a moment arm now of 2 plus 3 cosine 30. So I have 4 plus 3 cos 30. And the 40 is going to make a clockwise rotation, so minus that. And all of these sum up to be 334 Newton meters positive, which means it's clockwise. If I got a negative, counterclockwise. If I got a negative value, it would be counterclockwise. Why is that? Because I assumed that counterclockwise is positive. Okay? Okay. So this here is an illustrative example of how moment is, or how it works in some civil engineering applications. So what we have here, we have a beam and we have some force F that's applied on the beam. And what I want to show you guys is moment doesn't always cause a rotation, because remember, we're dealing with statics right now. And so our systems are staying still. So what we want to see here is there's actually a force applied, and instead of causing rotation, what we have is actually a resistance to rotation. So F here, it's going to cause the beam to rotate, right? If we're looking at point A, it would induce some clockwise moment about A, right? We would have MA equals force times distance, D, right? The distance from A to the force, right? FDA. Now, imagine if I remove this support B, if we remove this completely. We would see this would fall down and we get some rotation here, right? So this support B is resisting rotation. This support B here is resisting rotation. So a lot of times in civil engineering applications, we're talking about resistance to rotation or translation or movement in general, okay? I just want to bring this to your attention early because we're going to be talking about this a lot in our future concepts and in this topic and in the future topics, okay? So one trick or mathematical concept that we're going to use to figure out our moments is the cross product. And what the cross product is, we'll also talk about dot product, but what the cross product is it's basically the multiplication of two vectors. And here's an example of that. So we're saying vector C is equal to vector A cross vector B. And the magnitude of C, so that actual scalar quantity would just be the magnitude of A times the magnitude of B times the times the sine of the angle between the two vectors we're multiplying. So here's a pictorial representation of that. We have vector A, vector B, and the angle theta that acts between them. And the direction is perpendicular to the plane that contains A and B. And we're going to specify C, or the unit vector UC, using the right-hand rule. And so I've written this down here for you. It's going to be the magnitude of that AB sine theta times the unit vector in the C direction. Okay, so here are some cross-product laws of operation. We have the cumulative property, which means that A cross B is the same as saying negative B cross A. If we have some scalar alpha that's being multiplied in, all we have to do is say the scalar alpha times one of the vectors cross B is equal to the same thing as the non-scalar times the scalar times B, which is the same thing as taking it out all together. Okay, and here if we have 3, we have A cross B plus D. That's the same as saying A cross B plus A cross D. So we can distribute those in distributive property right there. Okay. So for our Cartesian vector formulation, what we're saying here, so let me pull back before we get to this here. Remember, C is equal to A cross B, right? Which is equal to AB sine theta times the unit vector in the C direction. So we can use this equation to find the cross product of any pair of Cartesian unit vectors. So for example, I'm going to show you what I mean by all of this here. For example, let's say we have I cross J. These are two unit vectors, right? The magnitude of the resultant, we're going to have I, J, sine 90, because we know that all of our Cartesian coordinate systems are 90 degrees apart, and then we know the magnitude of our unit vectors are 1, so we end up just getting 1. Pretty cool, right? And the direction is determined by the right-hand rule. So that's what we're showing you here. I cross J is just going to be 1, and which direction is it in? Well, it's in the direction of the third vector, which would be in the K direction. So I cross J is just equal to 1K. And that's basically what we've come up with here. So this is how we came up with that. Okay. Now, all the rest of these are come up in the same way. So what you'll notice here is any unit vector times itself, cross itself, is 0, right? I cross J, J cross K, K cross I is just the opposite unit vector that wasn't included. And if we switch them, we get the negative. Okay, so these results shouldn't be memorized. You don't need to memorize these. You need to understand them. And the reason I say that is because memorizing isn't going to help you. You need to have a good understanding of the cross product from mathematics so that when you're doing these problems and you have multiple moments and forces that are acting on the systems, you can really easily figure out which direction and what magnitude you're dealing with. okay? So we can also use this nice circle formulation. This is another way of remembering this. So I'm going to draw a circle here. Okay, and in the circle I'm going to write I'm going to write the j vector, and I'm going to write the k vector here, okay? And remember, we're dealing with always counterclockwise is positive, and we're dealing with clockwise as negative. That's going to be our sign convention. So anytime you're crossing counterclockwise, you get a positive result. So, for example, if I'm going from let me use a different color here. If I'm crossing I with j, it's going to be positive k because positive. If I'm let me do another one. If I'm crossing j with I, it's going to be negative because I'm going in the clockwise direction and the one that I didn't do, right? Okay, let's do one more. Let's say I'm crossing I cross k. I'm going clockwise, so negative j. So if we come up here, I cross k is negative j. So make sure you understand this little wheel. It's super helpful in just getting quick kind of values instead of having to actually multiply everything out. Okay. And then for Cartesian vector formation, this is how we can actually take the cross product. So we put the I, the j, and the k values, the x component, the y component, the z component, and then we can multiply all of these out using the determinant. Concepts of the determinant, which we'll kind of go over in the examples. Okay, so now moment of a force in terms of the vector formulation, we can basically express the moment of a force by just using the cross product. So remember, r is our position vector, so we want that perpendicular distance from point O to the line of action of the force. So this is our position vector, r. Times the force vector. So all we have to do is r cross f, and we'll be able to figure out the moment of about our specified point. Okay. So magnitude is given again by the scalar r multiplied by the scalar f times sine of the theta, which is the angle between r and f. And then the direction, we can also use the right-hand rule to figure that out. Okay. Okay. Now we have something called the principle of transmissibility that's going to help us solve some problems. So typically we use cross products when we're working in 3D because the perpendicular distance is not always really easy to find, okay? And it's not needed when we're using the cross product because we're just going to use this r, this position vector, instead of having to find that perpendicular distance, okay? So what we can do here is really, we can take the line of action of the force, and it doesn't matter which distance we're using, we'll get the same thing regardless. So any of those distances, any of the distances measured to point O, which is that line of or measured from point O to the line of action, can be used to figure out our R, and this is called the principle of transmissibility of a force. So we can think of F as a sliding vector basically that acts along any point on this line, and we can use any R to figure out what the moment about that point that we're trying to figure out is just by using any of those distances. Okay, and I'll show you that in a couple of the examples that we're going to do. Now, Cartesian vector formulation for moments, r cross f here. So again, rx, ry, rz represents the x, y, and z components of a vector drawn from point O to any point on the line of action of a force. Okay, and this is the determinant all multiplied out. So this is the same thing as this, it's just all multiplied out, so you don't have to remember how to do the determinant. I've already put it here for you to figure out. Okay. Now, for resultant, I'm going to do the same thing, just like we did earlier. Resultant moment is equal to the sum of all of the position vectors cross the forces. So that's all we have to do, is just sum all of those together, and we'll get the resultant MO. Okay, so let's try an example now. I want to figure out the moment produced by the force F about point O. okay? And I want to express the result as a Cartesian vector. So here, about point O, I have this force A. I also have this point B here. So it doesn't matter if I want to use R going from A or R going from B up. I'm going to get the same moment regardless of which one I use. So I'm going to show you that RA here is just equal to 12 in the K direction, right? I only have A acting in the Z direction. RB is equal to 4 in the I direction plus 12 in the J direction. So it's just easier to use A because I only have one component in that direction instead of having to use B, which has two components. So I'm going to go ahead and go with that. And I'm going to say, come down here, the force is equal to the scalar quantity of the force, the magnitude, times the times the unit vector AB, which is 2. I know that it's a 2 kilonewton force. Now, times here, the distance from RA to B, so I need to subtract the 2. Okay, so I'm going to go from 4I plus 12J minus 12K, right? This is RB minus RA, the difference there. And then I need to divide that by the magnitude, so 4 squared. And I end up getting 0.4588 in the I plus 1.376 in the J minus 1.376 in the K, and this is all in kilonewtons. Okay, and that's really it. This is the force, right? So now I need to just take this force and multiply it by that R, that distance, right? And again, I'm going to use RA just because it's smaller. So here my MO is RA cross F. And remember, you can use FB if you like. You'll get the same answer. I'm just going to write this out for you. You can go ahead and plug it directly into the equation, or you can actually just do the cross product from this. It doesn't matter, whichever one you want to do. Okay, and basically here I end up getting 0 times 1, negative 1.376 minus 12 times 1.376, and this is in the I direction. So I'm just plugging directly actually into this equation here. Minus 0 times negative 1.376 minus 12 times 0.4588 in the J direction, plus 0 times 1.376 minus 0 times 0.4588, and this is in the K direction. And I can simplify all this, and I get negative 16.5 in the I, plus 5.5 in the J, and this is in kilonewton meters. Okay. Remember, my MO, so this is a picture of it, my MO acts perpendicular to the plane that contains the F, RA, and RB vectors, right? That's according to the right-hand rule and according to the cross product, right? So MO acts at I and J, perpendicular to the plane that contains F, RA, and RB, which is basically then the K. Okay? Okay, let's go ahead and stop here for part 1, and we'll continue part 2 in the next